Today topic is bending moment diagram. For number one, for point load. No, sorry. Important 2 points. 1 number points. If there is a moment while drawing bending moment diagram, calculate bending moment twice just before or at just before and plus at just before moment plus at moment. Another point is at the location of the moment at the location of moment bending moment sudden changes in the bending moment diagram. These 2 points very important. Just note down, and when we solve a problem, then you can easily understood these 2 points. Suppose case 1 shear for point load bending moment diagram for point load at number. For point load, shear force is constant. Suppose C shear force is constant. So we know slope of bending moments diagram. Bending moments or rate of change of bending moments is known as shear force. So equal to constant C. The M equal to integration both sides dm into c into dx. This is constant, and integration both sides m equal to c1 into x into c. This is the equation of straight line. Straight line equation. So we can say for point load, bending moments, so we can say if the shear force is a constant between 2 points, if shear force diagram is constant between two points, the bending moment diagram is an inclined straight line. This is very important. For point load, we discuss about shear force previous lecture. Shear force is constants, but bending moment is inclined straight line. Suppose this inclined straight line or any two. Understand? Next, case 2, for UDM, uniformly distributed load. UDL, uniformly distributed load. We know for UDL, shear force equal to inclined straight line C1 x into C2 with dm equal to dx equal to C1 x plus C2. Integration and get C1 x square plus C2 x plus C3. This is the second order parabolic equation. So we can say, if another point, if shear force diagram is an inclined straight line between 2 points, so bending moment diagram is a parabolic between those points. Will be between those points. Understand? Case 3, shear force diagram for UVL, uniformly varying load. We know shear force for uniformly varying load is C1 x square C2 x plus C2, hence parabolics C3, and we know V equal to dm by dx equal to C1 x square C2 x plus C3. So m equal to C1 x cube plus C2 x square C3 x plus C4. So this is the cubic parabolic equation. Cubic parabolic equation. So we can say if shear force diagram is a parabolic, shear force is a parabolic, so bending moment between 2 points so bending moment diagram will be a cubic parabolic. Understand? uh, Draw a table. You can easily remember it. Shear force diagram, bending moment diagram, and there is a for point load. The nature of shear force diagram is constant or rectangular, and inclined straight line. For point load, uniformly distributed load in shear force diagram, inclined straight line, and this is parabolic. Bending moment diagram is parabolic, and UVL, for UVL parabolic. Shear force diagram is parabolic, and this is cubic parabolic. Bending moment cubic parabolic. Now a problem you can easily understand how to solve the problem of bending moments and shear force and draw their diagrams. Suppose this is a cantilever beam. And this endpoint 5 kilonewton x, and and here the moments clockwise sense moments, his value is kilonewton meter, and the distance from endpoint 3 meters, and this is 2 meters. Calculate the shear force, draw the shear force diagram, and calculate the maximum bending moments. First, step 1 is draw FBD. Step 1 is draw FBD, free body diagram. This is 5 kilonewton. This is 5 kilonewton meter, and here suppose this is point A, this is point B, this is point C. RV this is fixed support. That's why here x direction a reaction force and y direction a reaction force and a moments, and RAYB RBX and a moments MB X here. This is free body diagram. Now calculates here RBX equal to 0. So RB equal to RB. Now summation of Fx equal to 0. So there is only, so static, now applying static equilibrium condition, summation of Fx equal to 0, Rbx equal to 0. There is no vertical horizontal shear force, only here horizontal shear force reaction force is Rbx, so this is 0, and summation of Fy equal to 0, static equilibrium condition. Up, suppose up, we assume upward force is positive, Rb equal to positive Rb, and downward is 5 equal to 0, so Rb equal to 5 kilonewton. And moments, summation of MB, summation of MB, M about point B 0. So this is distance from here 5. So moment clockwise sense is positive. Assume this is also assume 5 into clockwise into 5. This is point A, this is point B. Point A to B, the distance between point A and B is 5. So this is 5, and this clockwise sense serves. That's why force into moment is force into distance is moments, and this is also clockwise sense, so positive 5, and this also counterclockwise or round, so minus MB equal to, so MB equal to 30 kilonewton meter. So MB equal to 30 kilonewton meter. So here Rb equal to 5 kilonewton, and here MB equal to 30 kilonewton meter. And what is, and step 2, shear force at this before shear force before, suppose here point load 5, so here shear force, calculate shear force twice, shear force before A 0, shear force at A, we know shear force positive left right, this is clockwise, this is negative left right. We calculating shear force from right side downwards, means positive 5 kilonewton 5, and shear force, there is no shear transverse force between A and B points, so shear force here a one force point loads, shear force, we calculating these right sides, shear force before left side, sorry, before B equal to 0 from and shear force at B, calculating these B points from left side, and left side upwards mean left side upward positive plus 5. So draw shear force diagram. Shear force diagram. Shear force is 0 at 5 positive. This is 5 kilonewton, and before B from here and at B this is also 5, so 5 kilonewton. This is positive plus, understand, first shear force before A 0, at A 5, and there is no shear force, there is no point load between at A and before B, so this is constant. And before now calculating B points before A from left side, before B is 0 and at B this is 5. This is SFD, shear force diagram. This is V versus X. Now bending moment diagram. Bending moments at here is a one moment, so there is calculated bending moment twice. Before bending moment before B is 0, bending moment at B now sign convention. This is sagging left right, this is positive bending moment, this is hogging negative left right. Now left side counterclockwise means negative 30 at B, negative 30. And now bending moments, here is one moment, so before C is minus 30, calculating from left side, bending moments at C